All right, ladies and gentlemen, tonight we are going to be focusing on distance and midpoint formulas. So what you'll need from me are your notes for your composition notebook, a blue foldable that you should have gotten from me in class today, a pen or pencil, and also a calculator. We will be working with some calculations, so if you so wish, you can grab a calculator. We're going to first look at this example here about finding distance on a coordinate plane, and this should be something that is review for you. So if we have this diagram or this rectangle on a coordinate plane that we have shown here on the left-hand side, and we're asked a question as something like written on the right-hand side, the measure from A to B, or the measure of line segment A to B, would just be this line right here. And in this particular diagram, it's super easy to figure out what that distance is, right? Because all we would do is count from this point to this point, how many units. So it would be 1, 2, 3, 4, 5, 6. So it's 6 across. And then if we were to look at line segment BC, we would have it from this point B to C, so 1, 2, 3. And you don't have to be writing this example down. This is just something we're going to talk about before we talk about the actual distance formula. So this is a little bit of review. And then we know that the opposite sides would be the same because remember, opposite sides of rectangles are congruent. So this left-hand side would be 3 and this bottom side would be 6. But what if we wanted to find the distance from A to C? Well, that's a little trickier when we're looking at a grid because we don't have a way to measure these diagonals that are cutting through these boxes. But some of you might recognize that I have a right triangle here, so a way that I could find the distance from A to C is if I set this up as a right triangle. So if we use the Pythagorean theorem, remember Pythagorean theorem is a squared plus b squared equals c squared, we would get 3 squared plus 6 squared equals x squared. 3 squared is 9, 6 squared is 36, 9 plus 36 is 45. And if we wanted to solve for x, we would have to take the square root of both sides. And 45 breaks down into a perfect factor of 9 and 5. So this becomes square root of 9 times the square root of 5. Square root of 9 is 3, and we have a square root of 5 left over. So that's what our distance would actually be for the line segment AC, is x equals, or AC equals 3 times the square root of 5. And as you can tell by the math that we did, there's no way that we could possibly count that from the picture. That last example, we had a grid, which was really nice to work with because when we had our rectangle, then it made sense how to count the sides and that we could find the diagonal. But for this particular example on this slide, we don't have a grid attached. So we have to think about how we could create a formula to find distance, a general formula to find distance. So let's use what we did on the last slide and apply it to this one. So we're going to create a right triangle, even though it doesn't necessarily exist on this coordinate. So we're just going to look at this right-hand triangle. So if we wanted to find the distance from point B to this right angle on the right-hand side here, if we wanted to find the distance of the base of this triangle, we would take the x value from this point, which is x2, and the x value from this point, which is x1, and we would simply just subtract the two. That's what we did on the last slide, right? We would take x2 minus x1. If we wanted to find then the distance from point A to the right angle, or the height of this right triangle, we would take y2, the y value of point B, minus y1, the value of point A, the y value of point A. And since we're looking for, overall overarching goal here is to look for the distance of the hypotenuse, which we're just going to label D right now. So because we drew a right angle, you guessed it, we're going to have to apply the Pythagorean theorem. And remember, Pythagorean theorem is a squared plus b squared is equal to c squared. And in this particular example, A or B is just one of my sides. So I'm going to write A as the side that I labeled in red. So that side length is x2 minus x1, quantity squared. And then B is that blue side, the height, which is y2 minus y1, quantity squared. And then our C is actually the hypotenuse, which is just d squared. So I don't know any of these numbers right now. I just have an equation written with all variables. But if I wanted to solve for d, I would have to, in order to get d by itself, I would have to take the square root of the right-hand side and the square root of the left-hand side. So then that would leave me with d equal to the square root of everything underneath the square root sign, the quantity x2 minus x1 squared plus the quantity of y2 minus y1 squared. And there you have it. This is our general formula to find distance when we don't have grid paper attached to our diagram. And ta-da! The distance formula was given to you in this little foldable that we created. So this formula, d equals the square root of all that gobbledygook, is on the front flap of the foldable that you got, and it's on the inside of the foldable. And you'll see this picture and this formula on the inside of your foldable. So underneath that formula, I just want you to remind yourself that the ordered pair x1, y1, and x2, y2 are coordinates or ordered pairs. So that's where these numbers are coming from. They're coordinates or ordered pairs given to us on a graph. So we're going to look at two examples of using the distance formula when just given points. So first let's write the distance formula. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And in our first example, the first set of points is x1, y1, and x2, y2. So just plugging those into our formula, we said x2 was 0 minus 4, taking that quantity squared, plus we're taking y2 minus y1. So we have 3 minus a negative 6 quantity squared, and we're taking the square root of that entire thing. So now we move down to just doing simple math. So 0 minus 4 is a negative 4 squared. Remember, we're taking the square root of this entire thing. And then we have 3 minus a negative 6, which would be 3 plus 6, which turns into a 9 squared. So now we have d equals the square root of negative 4 squared, which is 16, plus 9 squared, which is 81, and 16 plus 81 is 97. So now we have d is equal to the square root of 97. And it's at this point that we would want to look for any factors that are perfect squares that go into 97. But for this particular example, this is as simplified as we can go. There are no perfect squares that are a factor of 97. So let's look at our number 2. I'm not going to rewrite the distance formula. We're just going to plug in numbers right away. Remember that our first coordinate is y1, first coordinate or our first order pair is y1, y2, and second one is x2, y2. So we have d is equal to the square root of x2 minus x1 is 0 minus a negative 4 squared plus the quantity negative 8 minus 2 squared. And now we're just plugging and chugging. So 0 plus 4 is still 4 squared. And we have negative 8 minus 2 for a negative 10 squared. And we're still taking the square root of everything. And 4 squared is 16. Negative 10 squared is 100 square root of 16 plus 100 brings us down to our last steps. Square root of 116, because 16 plus 100 is 116. And now we have to think here. So what factors or perfect squares are factors of 116? And I found that 4 times 29. So the square root of 29 times the square root of 4 is in fact the square root of 116. So I broke it up that way. And now we know that the square root of 4 is 2, and the square root of 29 can't be broken down any further. So our final answer for example 2 is 2 square root of 29.